According to the cloud.
There we go.
Okay.
The infamous cloud.
Yes. Somewhere out there, this is being recorded.
Hmm.
Now, can you guys still see me?
I can see you on the bottom. Yeah.
Okay. So what I've done, I hid the video feed on here, so all I'm seeing is my slides. So I assume that's what's getting recorded. So not everybody's beautiful faces. We'll find out, I guess, later. All right. Well, Mike, do you have any exciting news to share before we get started?
Not really. Thank you, Rick, for presenting.
Welcome.
It's a good topic. We got quite a few people that were interested. I don't know about you guys, but been pretty busy. There's no, I mean, that's a good thing. I know a lot of people who aren't working, so very happy. But been busier than heck. And I don't know about you guys, but it's been a busy 3 months. Finally getting used to working from home, although I really want to go back to the office so I don't have to work so much.
Yeah.
So I don't know if that's all I got. And,
okay.
Go ahead and get started.
All right, great. Well, we're going to talk about Oracle data blocks is really what this talk is all about. So, which I'll be honest is becoming less and less important as we move to the cloud and things like that, because this stuff is kind of fading off into the ether. We're going to have less and less control of this kind of stuff as we roll forward. Although I think if you're a professional, it's still a good idea to at least know about this, because honestly, the magic of Oracle is right here in the data block. Without the stuff they do there, we wouldn't be able to do all the really cool stuff we do. You know, backup recoveries, all those kinds of things are really possible because of this. So we'll talk about the data block. What's a row? What does that look like in the actual data block? What happens when you update? That's kind of interesting. And we'll get into the myth of block sizes and what about bigger versus smaller block sizes? Does that matter and all that stuff? And then some really kind of semi-esoteric stuff is the block storage parameters. It's that's certainly something that's becoming in a very big way kind of unimportant these days. But this is me, blah, 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 blah. Okay. So, whoops, whoa, a little too fast there, VanDyke. So the data block, of course, is going to be the most common block in your database. There are other kinds of blocks. There are index blocks, rollback blocks, temp blocks, but really they're all about the data block. That's really what matters because that's where our data is stored, and that's what makes the database the database. So there we go. It's going to contain data almost always. Like I said, there are index blocks and temp blocks and things like that that are structurally similar to a data block, but they're going to contain other stuff. So their header and stuff is going to be different. So they're going to have different stuff in it. But yeah, a data block is going to have data in it. The default size for your database is unchangeable. Once you create the database, the default size is done. It's fixed. The only way to change it is to rebuild a new database. Now you can have multiple block sizes in your database. So I can have different sized blocks in different table spaces. Now, really that was only introduced when they introduced the transportable table space concept back in, I think, version 8. I can't remember that real well, but somewhere way back then. And they introduced this idea of being able to move a table space from one database to another, you know, just basically copy the files from one place to another. And that was really cool back then because moving data between databases was painful. So just by copying files was like, oh, wow, this is awesome. But then there was a problem of, well, wait a minute, what if I'm going from a 4K, which actually was kind of common back then, to an 8K or 16K database or the other way around? I can't have multiple block sizes in my database. So that really was like, oops. So they allowed you to have multiple block sizes. You have to create the table space for the particular block size. Now, on the surface, it sounds kind of cool, but it's really a pain in the neck because now you have to have a buffer cache for each different block size in your database. So if I've got, some table spaces that are 8K, which is the most common today, and then some that are 16 and 32, well, I've got to have a buffer cache for each one of those. And let's say the 16K block table space is barely ever used. Well, I've just allocated a whole bunch of memory space to this thing that I'm really never going to use. So it could potentially be really problematic. And I've never recommended multiple block sizes in a database. And we'll get into this block size business in a little bit and talk about, does it really matter? And there's a good old it depends kind of answer to that, of course. But yes, you can have multiple block sizes. But today, yeah, you're typically going to have 8K block sizes. I don't even know. Well, let me put it this way. The Exadata system I was on out in California, I'm pretty sure they were 16K blocks that they had. But, I don't know if that's just the common thing for Exadata or not. I haven't really looked into that. But yeah, the max is now 16 or 32K. Interestingly, VMS, the old digital operating system, could go up to 128K block size. That was the max of the maxes as far as I know.
Do you know of anyone who is actually using 32K blocks?
No.
I don't know either. I was just curious to see if they knew of anybody that was actually using it. And why would they use that versus, 16? Like, what are you doing that you need 32K?
Well, usually when I find people are using even like 16K blocks, they're believing a myth that we'll talk about when we get to block sizes coming up. But yeah, 8K is a really good block size. 16K, I guess, is a good size for doing strict data warehouse, and I mean strict data warehouse type of stuff. But 8K is really a great block size. It really is. So,
Yeah,
and we'll get into more about that when we get into the
I
block
actually,
size.
we just did a install, and they sent us the documentation, and they recommended 32K. I said,
Wow.
why? Why? And it was JD Edwards or PeopleSoft or something like that. And it didn't make sense. I said, we're going to leave it at 8. There's, there's,
yeah, we'll talk a little bit about the block size again coming up, but yeah, I'm not a big believer in giant block sizes. I don't think that's a good idea, and we'll talk about why. So anyway, let's dive into the block a little bit here, and there's some different parts of the block. So we've got the block overhead there at the top, and there's a common header area. Then there's a table directory. Now this is kind of a remnant from earlier days. Generally speaking, there's only going to be data from one table in a data block. But if you go way back in Oracle time, and I'm talking like version 6 and stuff, back then the only alternative we had for table storage were these things called clusters. Now they still exist, and you still can create a cluster, and you can put multiple tables into the cluster. And so you build the cluster key around the join key. So the classic example, of course, is employees and departments. So instead of storing those as two separate tables, we're going to store them together. So that's where this table directory comes in, where if there were multiple tables in here, it would talk about the two different tables or 3 or 4 different tables that are in the block. But generally speaking today, your data block is going to have one table in it. So it's kind of a, I don't know what word I'm looking for exactly, but it's a leftover from years gone by that, we used to do that. We used to have clusters. I personally have used them a couple times, and most every time I ended up going back to a regular set of tables with regular indexes because the cluster was just kind of a pain to manage and all that kind of stuff. So there you go. That's what the table directory is. The row directory is very important because the rows, as we're going to see in a moment here, grow up from the bottom of the block. So the first row is actually going to get inserted right at the bottom and then go up and up from there. And this row directory actually points to where the row actually is in the block. So that's a real important structure. That hasn't changed in 1,000 years, as far as I know. And then in between the row data, which is you see at the bottom, and it really does grow up from the bottom. I've done block dumps 1,000 times, and you can see it. You can see how the rows actually grow up from the bottom of the block. And then in between that is going to be some free space, and Oracle is going to manage that. And I don't know if you guys remember, like, operating system programming, and you had the stack and heap stuff, and you run into the stack overrun heap error, and that was always really bad. That's the same idea here. We have a stack and a heap in a sense, those two structures. The heap in this case is actually the bottom where the rows are, because that's kind of a heap-like structure. There is a structure to it, but each row is just thrown in there wherever it fits. And the stack is more the top, because that's kind of in a much more regimented way, if you will. It's much more layered. So very specific things that are specific parts of that. So it's more like a stack at the top and more like a heap at the bottom, if you want to get really fancy. So the overhead, going to be around 100 bytes. It varies a little bit by OS and particular features that you might have enabled, but it's going to be around that. It has basically information about what does this block belong to, and some transactional information. That's another important part that I kind of skipped over. So there's a transactional information also in the header to say which rows are locked and kind of by whom, although it's not absolute right there. It actually points to the rollback segment header that then has in it who is it that locked that row. The table directory, just talked about that. The row directory, again, talked about that. And this is where the row IDs actually point to. The row ID doesn't really point to the row. It points to an entry in the row directory, which then points to the row. And this is really one of the magical things about Oracle, because this really helps Oracle be very dynamic with how it stores and where it stores those rows. And we'll see that as we go through some of this stuff. So real quick, look at row IDs. Most of us are probably familiar with row IDs, at least the old row ID format, which used to, that had little dots in it, and it was really easy to see the different parts of the row ID. Today, it's a much more complex looking row ID. There's a row ID there in the raw, which is just looks like some alphanumeric string. It's actually a number. It's base 64, so Oracle had to come up with a whole bunch of letters to fill in the rest of the digits that aren't there from our base 10 numbering system that we use. And really that last thing that says row on it, that's actually really pointing to the row directory entry or slot number in the header of the block. So the first row in the block is going to be row 0, okay? And that means I'm going to the 0 entry in the row directory, look at that, and then that will actually point me to where the row actually begins inside the block. And the reason that this is so important is that row IDs never ever change, right? Once a row ID is assigned to a row, it's done. Don't get a new row ID ever unless you delete and reinsert the row. But the row ID itself is actually going to move around. Now, we could, I guess, just update the row ID every time the row moved. But that would be really bad, because where are row IDs stored? Well, they're stored in indexes, right? That's how we use an index. We go into the index, blah, 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 blah. Oh, row ID, we go get the row. Well, imagine that a row moves. How many indexes might we have to update every time a row moves? That would get really bad really fast. So these row IDs, generally speaking for a row, the row ID never, ever, ever changes. Now, somebody's probably going, hey, Rick, you can enable row movement, with a partition table, and, rows can move from different partitions and they get a new row ID. And you're right, they can. But generally speaking, they're not going to change unless you do that. And you should only do that if you really need to, because for some bizarre reason, your application might actually change the partition key of a row, which causes it to move to a new partition, which, really is something you should try not to do. But anyway. So we can dump blocks. I don't know if everybody's ever done this. It's a great thing that most DBAs love to do on a Saturday night, do some data block dumps and read through block dumps. No, not really. But Yeah, you can block it or block a dummy. You can dump a block and take a look at it. And we're going to do that here in a little bit. And I'm not going to go through every single piece and part of it, but we'll just kind of look at the cool stuff. And when you do this, by the way, there's a little trace identifier you can set prior to doing this, and it can help you find the actual trace file. So as a matter of fact, and I forgot, I should have brought this up already, Crump, I'm going to have to jump out of here, get to that file. So Mike, do some little song and dance while I'm finding this file. Mike, you're not helping me. Hey, you go off on a
I
went
was
to
my
the
mouth
bathroom.
was,
Okay, I get it.
my mouth was full with food. I didn't want to spit out. Sorry.
Okay, I've got it. So let me switch now. How do I switch to this? So I've got to what? Stop share, and now share, and this thing. Okay, does everybody see a text file?
Yes.
Okay, cool. So this is the block dump, and we're going to talk about some of the pieces and parts of this coming up in the slides, but I just wanted to see it, let you see it in the raw. So here's the top of it, and like almost every dump or trace file in Oracle, the top looks very similar to most trace files. It's got some preamble-y kind of stuff in there telling me the version of Oracle, the OS, you know, who is running the query or the whatever. So I'm on this node, which is my laptop, or my old laptop actually. And then we get to session information down here, and then we have the block dump. Now, from about here up to there is the block header, okay? So this is all the header information about the row or the block. And this has been actually formatted in the output of this, so it makes it look a little bit easier to read than the actual raw dump or raw trace file, or I'm sorry, the raw block file. But yeah, it's got all that kind of stuff in there. And I'm not even gonna pretend like I know what all this stuff means, but it's really cool. It looks really awesome. So if you want to impress somebody, just dump a block and bring it up on your screen, and they'll be like, "Oh, wow, what's that? Oh, it's very complicated," you know.
You just
Anyway.
mentioned something that I just thought of. There's the table. I think it's $BH. Is that? I'd never realized, but BH probably stands for block header.
That's exactly what it does. And $BH is a great way to view all the blocks in the buffer cache.
Yeah.
Yeah, that's exactly what it is.
Hmm.
You're right. Bingo.
Yeah.
Now down here is the data. This is the data block, you know, the real data. And this is an 8K block, and you can see it goes on and on and on and on. And, you know, there's all the data. Now this is kind of got garbage in it because, you know, it's mostly nothing. The only data that's really in this block is actually down here. These are the first 3 rows, the only rows in this table. You can see there's first row, second row, and third row, okay? And those are, it's not a joke. That was the first row inserted, the second row inserted, and third row inserted. And you can see that the first row really is at the very bottom, then the second one, and then the third one. So they literally do grow up from the bottom of the block as you insert data in. And then we're going to see what happens when we do updates and all that kind of stuff. But you can see that for the most part, this particular block, you know, it was allocated, and you can see that Oracle didn't like scrub the data. You know, there's just garbage out there that was just happened to be on the disk at the time that this block was allocated. So it's not like when new blocks are allocated, they're cleaned up and it's all zeros. It's whatever happens to be there. But the only thing that Oracle is ever going to look at in this block of these 3 rows, because that's the row directory entries, which are way up here. And they are, where the heck are they? I actually used to know this stuff. It's not these things. I know that. Crump. Anyway, it's in here somewhere. They actually point to those 3 rows and those 3 rows only. And also at the very bottom here, you can see Oracle does dump out for us the raw version of those rows. Okay, so here's the first row, and you notice it's table 0 Remember I said there's, for the most part, there's only going to be one table in the block, and that's going to be 0. That's row 1, which of course is 0, row 2, which of course is 1, and then row 3 is of course 2. And then this shows the data in those. And notice that this column is actually a null. And we'll talk about how Oracle stores nulls in the block and everything like that coming up real fast. And yeah, here's the blocks information. There's some trailing information to talk about who this block is and all that kind of stuff. And the transaction ID, that's a last transaction that modified this block. Okay. Now let's see if I can get back to the other, to the everybody see that again?
Yes, sir.
All right, we're rocking and rolling. I'm almost like I know what I'm doing. Okay, let me actually put this in presentation mode. There we go. So let's talk about the row. Again, another really cool thing about Oracle, and what makes it, I think, super awesomely cool is the row itself and how it's structured. So once again, there's a header part of the row. There's a little bit of overhead, just like a byte or two that just has some, general information about the row. Then this is where it gets really cool, okay? There's a number of columns that are represented in this row. Now, this row is part of a particular table. That table has a logical structure of, let's say, 15 columns. But what this number of columns represents is how many columns are in this row. Now, the reason I want to really stress this is how you and I can save a ton of space in our database by structuring our tables correctly. If you have columns that are almost always null, put them at the very end of the table definition. And it matters because then, as we're going to see in just a few moments, Oracle won't store anything about them at all. So for example, if this row only had 2 of the 15 columns, the number of columns would say 2. And there would be, and for each row, or I'm sorry, for each column, there's a column length, and then a column value, then a column length, and a column value. And so Oracle would know as it read this row that it's going to read one column, a second column, and that's it. There's nothing else for this row. Anything after that is either another row or junk or something, but it has nothing to do with this row, okay? And that is extremely powerful. And I know of some databases where they have made significant savings in storage just by restructuring their tables and putting all these columns that were null most of the time at the end, and all of a sudden, they've saved, gigabytes of space by doing that. It may not seem like much at first, but you start doing that hundreds and millions or hundreds of millions of times with these tables, and all of a sudden you've saved a ton of space. So it's really a cool thing that is, I think, again, built into this structure that is super cool. Another really cool thing, and it's not really highlighted here, but in the row header, the overhead, is the locking mechanism Oracle. So when you and I lock a row, we actually set a byte in the, byte in the row header to say that we've locked this row. And that's why you never run out of locks in Oracle, because every row has a lock byte associated with it. So you can't run out of locks because every row has a lock in it already. And there's no reason to escalate locks and things like that. So some really powerful stuff that's built into the structure of these rows. Notice, by the way, there is a cluster key down here. If it's a cluster table, that would help us. That's how we put together the data for that same cluster key, that join key thing, and put all that data back together. Again, very rarely do we use clusters at all anymore. I kind of think that they'll eventually go away. Oracle, one of the reasons Oracle couldn't get rid of them is they were still in the data dictionary. That is going away. So there's fewer and fewer tables in the dictionary that have clusters in them. So I wouldn't be surprised if in some future version, the clustering goes away completely. Although maybe not, you know, because there might still be application software that uses it. So it might be one of those dinosaur things they just have to keep around. The other interesting thing is that if this is a chained row, meaning that the row is bigger than what they can store in a row, then it's going to be chained. There'll be multiple pieces of it. Each piece, for example, can only have 255 columns. So if you've got a table with 400 columns in it, you're going to have multiple row pieces. And so you're going to have a chained row, period, unless you don't use most of those columns. You're going to be much chained to every row in the table. But usually a row just has one piece, and that one piece is in a block. So the columns, just kind of to reiterate this, there's the length and the data, length and data, length and data. And what's cool is, again, about these nulls. Now, if a null is in between two non-null columns, then it just has a length byte. But if it's a trailing null, nothing is stored at all. No data whatsoever is stored for that trailing null column. So that's where you can really have some powerful stuff going on in your row data. By the way, that's a picture of my son at the Madison, Lincoln, no, not Lincoln, the Madison Memorial in Washington, D.C. Get it? Column. See, he's next to a column. Crack myself up. Anyway, so this is my test data, little tables. I create a little table space, create a little table and put these 3 rows in it. Woo, very exciting. So a couple of things that I want to point out. First of all, we have a column here that's a null in between 2 non-nulls on the first row. And the second row has 2 trailing nulls. And then the third row has actually the word null, not the null value, but the word null. So let's see what happens with all this stuff. So this is just looking at that same trace file we just looked at. I'm just focused now on the data itself in the block. And I've kind of done a select up here at the top, which has the rows as you and I would select them. And then we can look at the row data in the block. So once again, the first row is really truly at the bottom. And you can see there's first row, know thyself, and the other columns, or the other column is null. Okay, now it's in between these two. So we're going to get into how is it represented in this data over here. Then we have the second row, and it just has the number. Now the numbers are stored in a binary compressed format. So the length of a number that's stored is actually the number of digits divided by 2 plus 1. So that's the length that's stored in there. It doesn't come up as a number here because it's not the ASCII values of those digits. It's a numeric representation in this binary compressed format for that value. So it shows up kind of as weird dots over here, but it's represented in this data over here in these bytes. And then the last one, notice we have the word null. And if you look, yes, it is the word null in the data as well. Okay. So let's dive into that a little bit. And what's something I found that's interesting, this has to do with physical storage and how the read-write algorithm works, like at the quote unquote disk level. But you'll notice that things are kind of stored backwards. Okay. So if we look at these sets of bytes for each letter, notice that we have E, F, G, H, but it's actually stored H, G, F, E, okay? And it just has to do with the way that it lays it down and rolls it off the disk, why it's kind of in a backwards order. So it's kind of, first time you look at it, you go, wait a minute, that's backwards. Well, yeah, it is, but that's how it's stored. But when it comes back, it's actually going to be in the right order. So kind of an interesting little thing. Now let's take a look at that first row, because remember, that's the one that kind of has this mysterious, null value in between those 2 non-nulls. So let's break it down a little bit. So here's the beginning of the row is actually up here. Okay, the 2C actually represents the start of the row. The 01, remember they're backwards. So 2C is the beginning. 01 is the lock byte that I talked about. And 04 is the number of columns. Okay, so there are 4 columns in this row. And the first one is first row. Then there's a number, which is represented here. Then there's, well, that's first row, it ends there. Then there's the number that's here. Then we had the null, okay? Now notice the null only has the length byte and it's an FF, okay? So that's interesting. So you probably would have thought that if it's a length byte of 0, because a null is 0, right? There's no length to it, it would have been 0. But no, it's FF. So that signifies a null column in between 2 non-nulls. Oh, okay. And then the last column would be starting here with the O or C0 or OC, sorry, 12, which is then the know thyself, again, stored kind of in this backwards kind of format. So I don't know what you guys, but I thought that was kind of cool when I first really started digging into this, actually many years ago now, and figuring out all this fun stuff with how it's stored and stuff like that. So FF signifies a null in between 2 non-nulls, okay?
Kind of reminds me of the days when we had to look at core dumps to figure stuff out.
Yeah.
Mm.
Good times.
My grandfather told me all about it. I'm not that old.
Yeah, right, sure. Now let's dive into this length byte thing a little bit, because hey, wait a minute, Rick, you know, with 1 byte, theoretically I could store, you know, I could represent a length up to 255, but you just told me that FF represents a null, so how do I have longer columns? Well, as soon as the column is greater than 1,000 characters, I'm sorry, greater than 254 characters, Oracle goes to a 3-byte, excuse me, a 3-byte length byte, okay? And the first byte will be FE, and that tells it, oh, the next 2 are going to be the actual length byte of whatever's coming up, okay? And then you'll have that. So here we can, now I used the null in this case so I could see, you know, where the next thing was, and that is the length byte of this next column, which in this case happened to be 1,000 characters. And then, so I had the FE telling me that, oh, these 2 bytes are actually the actual length bytes now. And so those 2 together are the length. Yeah, actually, I'm sorry. It's once the length is over 250, Oracle goes to this multi-byte length byte. So as soon as the length exceeds 250, you get a 3-byte length byte instead of just 1. Ooh, ah.
Interesting.
Yes, very fascinating, I know.
Well,
and
no,
formatted rows. Sorry?
It's kind of interesting that they just arbitrarily chose 250 rather than the 254.
Well, actually, it's not, because 254 is what they use to actually designate that the next 2 are the length bytes.
Well, then 253 then.
Yeah, exactly. I mean, you know, where you make the cutoff. Yeah.
Either way, just somebody said, nah, let's use a round number.
Yeah, somebody like 250, I guess. I don't know. Okay. This is the rows in the trace file. We already looked at these, but that's the same representation, but it's in Oracle's formatted sense. Look at the data, but it's the same stuff that we just saw. Now it is put out nice and a little prettier to read, but it's really all the same data. Now let's talk about chained and migrated rows real briefly. Chained rows is a row that doesn't fit in one block. It has multiple pieces. It also can happen when you have more than 255 columns that will automatically cause the row to be chained. Even if the chain row piece is in the same block, it'll still be a chained row. So There's not much you can do about chained rows. You've got really long rows, so there you go. There's no way to fix that. You could, quote unquote, go to a bigger block size. Maybe that'll help. You know, and that's one valid reason to go to bigger block size. You know that your average row length is just huge. And so sure, I'll go with a bigger block size. I should keep all my rows, you know, more of them in the same block and not chained across multiple blocks. That is one valid reason I can see for having bigger blocks. But other than that, I really don't see a good reason to go to much, you know, to big blocks. Now, migrated rows are different. They still actually fit in a block. They just don't fit in the block that they started in. So remember, an insert's going to put it into a block. Now we grow the row through updates. All of a sudden, the row's too big and it moves out. Now, these you kind of want to fix because the row ID doesn't change. The row ID is still pointing back to the original block. But when it gets there, it doesn't find the actual row. It finds, in effect, a new row ID that points to where the row really is. And that's problematic, especially with index lookups, because your index now always has an extra hop to find the row because it went here, oh, it's not here, it goes to a new block. Now, invariably, somebody will usually ask, hey, Rick, what happens if it migrates again? Do we get another pointer? Actually, no. Oracle's smart enough to go back to the original block and update that pointer to point to yet the new block. So yeah, migrated rows aren't great. It'd be great to fix them or clean them up, but they aren't horrid in that you don't have like 5, 6 hops because this row had to migrate 5 or 6 times. So fortunately, there's always just one hop. So that's kind of the good news with migrated rows. But yeah, it's an extra hop. So if you can clean this up, that'll be good. Now, how do you clean it up? Well, there's a couple of different ways. Obviously, you can just like export, import the table, something like that. Because the rows get inserted when you go to re-import it, they're never going to be migrated at insert time. Either a row fits in a block or it doesn't. And if it doesn't, it finds a new block until it can fit in a block, and then it puts it in that block. The other thing you can do is do the analyze table list chained rows. That will actually list both chained and migrated rows because both chained and migrated rows have a row pointer associated with them. And that's what the chained rows mechanism is looking for, rows that have a pointer associated with it. Now, this is where you've got to be smart enough to know if they're chained or migrated. So, because it's going to give you a list of row IDs of all these chained or migrated rows. Which one are they? Well, if you know your rows are really kind of small and they should all fit in a block, then you can feel pretty confident those are all migrated. But if you know it's possible that they could be chained, well, now you might have to do a little bit more investigation to figure out the actual rows, look at them, see which ones. And if most of them are migrated, okay, great, let's do something. So now that you've got this list of row IDs, there's something really, it's kind of a simple process, really. But basically what you do is you grab all the rows out of the table with those row IDs and put them like in a temp table. So, select from table where row ID in that big list. Now you delete all those rows in that original table with that same row ID list. And then you take that temporary table and put them back into the table. Boom, done. Now, obviously, those rows are going to be unavailable for some period of time while you do this. So there's, quote unquote, some downtime for the table while you do this. But, if it's problematic, and it's kind of hard to tell for sure if that's problematic or not, but if you have some a downtime period, whether it's planned or unplanned, and you can pull this off, it might not be a bad idea to clean that stuff up. One way you can help minimize the fact that this happens is % free, which we'll talk about a little bit later. Higher % free leaves more free space in the block, should mitigate migrated rows. Now, let's talk about updates, because this is really cool, okay? First of all, if I update a row in such a way that either the row length or a column length, any column length changes, then the entire row is rewritten into the free space of the block, okay? So if I change the row, let's say I do an update and I change 2 columns, one of them got 2 characters longer, the other one got 2 characters shorter, Well, the row length didn't change, but column lengths did. So therefore Oracle says, oh, okay, I'm just going to rewrite the whole row into free space. So you notice here, the original row was down here. After my update, the row is now up there with the new updated value, this XXX, where it used to be 102. Or I'm sorry, it used to be nothing, actually, I'm sorry, it used to be null. So now I put a value in there. So all of a sudden, both a column length and a row length change, bang, writes the whole new row up there. Now, if I do an update where neither change, the length of no columns and the row stays the same, it's an update in place. So here I updated the first row, which was know thyself, and just changed it to thyself know. And the row stays right where it is. Okay, Rick, that's kind of cool, but so what? Okay, here's the so what. This actually lends a little bit of credibility to having fixed length fields, i.e., char fields in your database. Let's say, just as a kind of an idea, you have a status field on a column, a row, and it's on all the rows in the table. And you do some ETL process that these rows go through a whole bunch of different things while they get through this process. And that status field keeps getting changed all the time. And just for fun, let's just say it's a value that could be from 2 to 6 characters. And so, and because you're, a good old Oracle kind of guy, you created the char, varchar 2 length of 6, or maybe even padded yourself and said 10, just in case it got bigger in the future, right? And now what happens, of course, is as that thing changes, even though maybe nothing else in the row changes, it's just that it's gone through some step of the ETL process, but you change that status field to let you know where it is in the process. So if something breaks, you can start the process over again and only process the rows that are of certain status, that kind of thing. Well, if that field is like going like this, that could be a lot of manipulation inside your data blocks going on with these rows kind of moving around and crunching and doing all this fun stuff. But if I made it a char 6, as soon as it was not null, it's 6 characters and it never changes. So something to think about. I'm not saying you should run out and change all your char data to some, varchar data to chars, but it does lend some credibility to some columns. It might be beneficial to have them as char fields instead of the classic varchar 2. Varchar 2, I still believe, should be the default, quote unquote, character data type, but there are times when char might actually make sense.
Oops.
Okay.
Hey, Rick.
Yes.
Rick, when the row moves within a block, does it does the space it vacated get reused, or
eventually? Yes.
Does it have to have another row that has the same length of space that it vacated? No. So it's not
So
looking for contiguous space.
Yeah, if we insert another row, it's going to go on top of second row, okay, no matter how big it is. What's eventually going to happen is this data is going to grow and get close to the header, right? And then Oracle is going to do what's called garbage compaction, and it will push all that down. So all those old rows that were, existed in between the real rows will eventually get compressed into, and the data will get rewritten over those old rows and they'll disappear. So yeah, those rows, this second row here, this one at the bottom, will eventually get written over. And if everything stays the same, third row will eventually overwrite second row, if we just kept inserting new rows on top of it. Does that make sense?
A lot of sense. Thank you.
You're welcome.
So then there would be something in the row header that would mark it as not the real second row?
Well, no, the second row now points here.
Okay, so
there's no pointer to this space.
It's just a lack of pointer to that location.
Correct. Right. Because remember, it knows the start location of every row in the header, and it knows how many, and once it gets there, it knows how many columns that represents, and it can find the end of the row.
Right.
So the garbage compaction is actually a pretty complex process because it's got to figure out what's junk and what's not, which is why Oracle waits till it has to do it. I always joke that the Oracle, kernel is like your teenage son. Okay, if you've got a teenage son, you know, if you ask him to do something, what does he do? Well, first off, he does nothing. And then when he finally has to do it, he finds the easiest, least amount of work possible to get that job done. And that's how Oracle works. Oracle says, I'm not going to do this garbage compaction until I absolutely have to. It's going to be a pain in the ass when I do it. So let me just put it off as long as I can. And then, oh, crap, I got to do it. So here we go. Okay, and it gets it done. So it just waits until it absolutely has to, and then it compresses all that. Because it is a complex process, because you're right. You know, how does it know what's junk and what's not? Well, it's got to figure it out. And that's where it gets to be, you know, that's why it waits until it absolutely has to. You know, a block may be in your database forever and never go through garbage compaction because it just, you never got close enough to the header that it mattered. And then other blocks, you know, they're getting compressed, you know, every day. But hopefully it evens out that most of them aren't getting compressed very often at all.
So it gets compressed before it goes on to the, or comes off of the free list?
Okay, so free lists are kind of interesting now. Okay, first of all, compression is
Sorry,
not,
I said compressed, I meant garbage collection.
yeah, the garbage collection can happen at any time. It's even possible, although kind of odd, that it'll happen during a select, because maybe some sort of update took place and it didn't recognize at that moment that it was too close to the header or something, and you select it, and all of a sudden it says, oh crap, I need to do compression, you know, do garbage collection. So garbage collection can happen literally at any time. Now, Oracle does keep track of the overall free space in the block, and now there's no longer just one free space or free list. There's 4 free lists that are managed now, and a block on the free list will have at least that much free space, and each free list has a percentage assigned to it, and I forget what they are right now. So each block will be on a free list saying, I have at least this much free space in it. And then when inserts come along, it'll go to the one and say, hey, I need about this much space, and it'll try to go to the right free list and hopefully find the block quickly on that list that it'll fit into. But yeah, this mechanism doesn't really impact directly the being on or off the free list. This is just a matter of when I get too close to the header and I want to insert something new, there is actually enough space in the block. It knows that, but not enough free space. It pushes it all down and says, okay, now I can put it in. Good? Does that make sense?
It does, thank you.
Awesome. Okay, so let's get into the myth about block sizes a bit. General advice, small block size for transactional, big block size for data warehouse. Probably everybody's heard that at some point, and if you haven't, you just did. That's some old advice that's been around for 10,000 years. I mean, I don't think it's been around for a long time. It's not necessarily bad. There's actually some reasons behind that, and so there is some validity to that. But why? Why is there validity to that? Well, why is a smaller block size good for transactional systems? Well, this is kind of an interesting thing. And if you think about it for a few seconds, it actually makes sense. There are going to be fewer rows per block because they're smaller. Okay, that's cool, Rick, but why does that matter? Well, there's these things called ITLs, which I kind of glossed over earlier. That's the transactional information that's stored in the header. Well, there can only be so many of those transactional entries in the header. As a matter of fact, the max is 255. So by having fewer rows, the ratio between ITL entries and rows is better, i.e. there might be, in effect, one ITL slot for every row in the block, which might be good in transactional systems where we're doing small row manipulation, i.e. we might be just updating a row in a table. And all of us might be updating a row in the same table. Well, that means we're all going to need our own ITL to do that, because that's how we actually lock the row in Oracle. We take out an ITL, and I said there's a lock byte in the header of the row. That actually points to the ITL that has that row locked, okay? Now with one ITL, I can lock one or all of the rows in the block, but I got to have an ITL to lock any row. Well, if I run out of ITLs, I got to wait, and this can be problematic. I forget the wait event. Mike, do you remember? ITL something. Wait a minute. That'll tell you that you're waiting for ITL slots. And here's a really bad thing about waiting for an ITL slot. You get assigned a slot. And until that slot becomes available, you wait. It doesn't matter if other ones are available now. You wait for that one. Okay. So if you're unlucky and get stuck behind somebody that went to lunch and decide to go home, they may never come back and commit, and you're just sitting there waiting for that ITL. That's really sucks. I just put a plug. So that's cool. That's good. Now, what about bigger block sizes? Well, now we have a lot of rows per block. One of the advantages of that is that indexes can be shorter, i.e. their height can be smaller, which theoretically is a good thing. And also, it's not too bad for data warehouses because A, we don't usually lock rows on a transactional-like way. We don't have a process locking individual rows. We have one update process that updates everything or inserts everything or something like that. So the fact that there's not a good ratio of ITLs to rows, not a big deal because we don't have very many transactions in the block. So there is some validity to this, okay? But what about performance point of view? So one of the things that folks like to say is that, oh, especially for big blocks are better for indexes because they'll be shorter and faster. Well, let's do some number crunching. Now, this is on my little laptop, so this is just a representation of the kinds of things that can happen. As I say, your mileage may vary. But this should give us at least some data points, shall we say, to kind of figure out if this is a good idea or bad idea. So let's start with the good old index scan. And we're doing a 4, 8, and 16K block. Okay. So the table, it's an 8K block. It's got 9 million rows in it. So at least it's not, you know, the emp and dep table. And it's got some 130,000 blocks. It's about 1 gig in size. Ooh, okay. Now, if I create the index in a 4K table space, it has 4 levels and it has that 197,000 leaf blocks. 8K, 3 levels, 16K, 2 levels, and the numbers of leaf blocks, as you can see, go down because we're able to put more and more entries per block of the index. So of course the index keeps getting smaller. It's actually the same size. We're just storing it in bigger pieces in, you know, the blocks. Okay. So there, you can see that clearly there's a reduction of the number of blocks that are going to be scanned when we do an index. So if we were to scan, like do a fast full scan, or sorry, a full scan across the bottom of the index, we'd touch a lot fewer blocks as we scan across the bottom. So that leaf block, you know, going down is potentially a good thing. The height going down is also potentially a good thing. So let's see, does it matter though from a performance point of view? So if I run some queries against this and I look at the time, now that time is in microseconds, and I ran this multiple times on my laptop. So this is a representation of that. It's, you know, if you will, an average of all those runs. Notice the time doesn't really change at all. The time to do this scan really was about the same, okay? So no real advantage from a real performance point of view. That's where I come from. A performance point of view is how much faster is it? Well, you know, it was 1.2% faster at 16K versus 4K. Well, you know, that's not enough for me to get excited about. I'm sorry, but, you know, come on. That's just, you know, yeah, you know. So, yeah, not really much here to get excited about for, you know, the speed of using that index. Now, again, this is a relatively small table in today's scheme of things and all that. Could this, you know, be a much bigger savings with, you know, a Galapagos table or something? Maybe. But even this should have shown some, you know, tangible improvement going from 4 to 16K, but it didn't. Okay. So when folks start arguing with you that you need bigger block sizes for your indexes, push back and say, hey, you're going to need to prove that to me because I think you're going down the wrong path here. And they probably are. If you're really looking for some big improvement gain in performance, that's probably not it. Sure, that might help a little bit. But remember, if I have multiple block sizes now, so let's say all my data tables are 8K and somebody wants 32K block sizes for their indexes, now you got to manage those two different things. And, it just adds another layer of overhead that's honestly, I don't think worth it. Okay. So, yeah.
We, the same person who suggested I think it was 32K block size, was saying, well, we're going to pure now, which is, it's all SDD drives. It's not, it's much faster now. And their argument was, yeah, well, that's kind of what I said too. But my question to you is, with the advent of this new storage, SDD drives where it's just virtual, no moving parts, does it make a difference at all?
Well, I mean, all these numbers would be faster, right? I mean, all these lookups would be even faster. Just cut them all in half, basically. Think of it that way. So, okay, great. I still would probably have about the same ratio of speed increase going from 4 to 16K. The number would be different in these two. They'd be, say, maybe 10,000 instead of 22,000. But okay, great. But that didn't change anything. I don't think the fact that they changed the hardware, quote unquote, where the disk is stored makes a difference. Most IO channel systems are built on an 8K mechanism, right? When you read and write from a IO device, it's an 8K thing kind of going back and forth. So why not just work with the blocking mechanism of the IO device, which is 8K?
Yeah, I agree. I mean, I stuck to my guns and stuck with 8K, but it was, they kept on saying, well, you have pure now, and
So what? I'm sorry, but seriously.
It is faster, and it is pulling more data faster, but that doesn't change some of the statistics that you're pulling back here. It's just that it's coming back faster.
Yeah. I mean, this is America, and if a little is good, more is better. I get it, but seriously, I really, other than I was talking about before, where you have really big rows, then maybe a 32K block actually might be justifiable. And by the way, I'm not even talking about blobs and clobs and all that stuff. Those are stored completely differently anyway. So don't even that doesn't really play into it. I'm talking about regular old rows. Yeah. If you have regular old rows that are really, really long, maybe a 32K block would help a little bit. But again, we're talking about way in the weeds here, trying to get some performance benefit. Yeah. The reality is, and we all know this, the reality is you got to tune your SQL to really get good performance. I don't care what you do at the OS level and whatnot. If you've got crappy, SQL, this kind of stuff isn't going to save you. It might make it look less painful, but the real problem is you got to tune your SQL.
Yeah, I have a phrase, and I say this: you can have the fastest racehorse in the world, but if it's pulling a piano behind it, it's not going to be very fast.
That's right. That's right.
Piano being the the queries and soft.
Yeah. I always joke that if you have a great car, but it drives on square wheels, it's really not going to perform well. Same idea. Yeah. So now let's do a full table scan, just kind of round this out. So now I'm going to take that same table, put it into a 4, 8, and 16K block, and notice that the number of blocks that the table is stored in goes down. Now, of course, the size of the table actually is quote unquote the same. It's just that the number of blocks it's in are getting smaller. So definitely, again, significant reduction in the number of blocks being stored. So that should help a full table scan, right? Well, again, not really all that awesome, okay? The time, interestingly, when we go from, I thought this was fascinating. Notice that, okay. So the time it processed for the 4K was 11 million microseconds, yet for the 16K it was 14 million. So it actually was taking it longer to process, the time to process took longer as the block size got larger. Now the logical IOs went down dramatically, which is cool. And that's a good statistic that we like to use to measure, how well a query is, because fewer logical IOs is generally good. But notice the time. So now this may be a function of my laptop more than the database, because maybe my laptop just, couldn't process these blocks fast enough, right? So that might be a function of my laptop not being able to process a 16K block anywhere near as fast as it could process a 4K block. But it does show you that even though I'm processing fewer blocks, but I'm processing the same amount of data, it actually takes longer to read a 16K block than it does a 4K block, which makes sense, okay? What's interesting though is that you would think that the reduction in blocks would somehow counteract the fact that it takes longer to process that 16K versus 4K, but at least on my little laptop, that didn't turn out to be true. So interesting. Again, your mileage may vary, so maybe you'll see that you get some better times even though you're having bigger blocks. So this could have been, a artifact, if you will, because of my little old laptop doing this. But I expected, well, actually, I'll be honest, I did not expect this. I thought at least the time would go down as I went up, not go up. So that was kind of fascinating. And notice the 8K was the worst, which is kind of bizarre also, So, fascinating. But anyway, all of this kind of shoots holes in the whole idea that I go to a bigger block size, I'm going to get better performance, I'm going to get better throughput. Not necessarily. If somebody, again, comes to you and says, oh, I need bigger block size for better performance, say, you better give me some test cases that prove that out, because probably not. Probably not. And even if it does, it's probably going to be minuscule compared to doing something like tuning the sequel that is god-awful to begin with, okay? That's where you're going to get your big bang for the buck, not doing crazy stuff like storing your tables in 32K blocks or 16K blocks for indexes and stuff like that. I've been to sites in the past where they'd say, oh, we put our indexes in bigger blocks because it's faster. And I'd say, well, how much faster is it? I'm curious. And they go, well, it's faster. Like, is it 2 times as fast? What are the numbers? Oh, it's just faster. So that tells me they didn't test. They just put it that way, and they have the perception that it's faster. So, it's wonderful. Anyway. All right, storage parameters. Percent free is probably the only one that you're going to play with at all, because percent used is pretty much gone. Okay, especially if you're using ASSM, which pretty much everybody is, if you know it or not. Percent free, as I mentioned before, higher values there could help reduce migration. Won't help with chaining, because that's just the function of the row length, but it could help in reduce migration of the rows. So that might be one you tweak a little bit so that you don't have as much migration going on. And if you know right up front that rows start in your database, or in that particular table, very small but grow over time. They only come in with like 4 or 5 columns, and they're pretty small, but by the end of the day or the week, they're going to have 30 columns and are pretty big. Yeah, you might want to set this, to like 15, 20, maybe even 25%, maybe higher even, because you know that those rows are just going to grow and grow and grow. This is how they work together, which is kind of, again, archaic at this point. Basically, the row data as it grew up, once it hit percent free, it would go off the free list. Then as it shrunk down, it would go back on the free list. Now, the way it works is The blocks are kind of always on a free list. There's just 4 different free lists, I think, by default. I don't know if that can be changed, but there's 4 different free lists, and there's a minimum amount of free space that the block has in it on each one of those. That's what ASSM does now. So it's kind of a better way to manage the blocks, because you don't have and you don't have the contention with the free list, which was problematic in some shops, which is why some shops would create free list groups, even if they weren't on rack, because that would give you multiple free lists per table. This now automatically does that, so you don't have to worry about it. Some other fun things that are, again, are becoming pretty much obsolete. Knit trans, how many trans slots to have in the block? Default is 1 for tables, 2 for indexes. The idea is that they know that indexes are likely to have more transactions per block, because there's lots more index entries per block than a table. And this, again, you might want to raise this if you know that there's going to be a lot of transactions going on in your database. There's a very good chance that there's lots of transactions hitting the same table, hitting the same block at the same time. You might want to bump it up. You used to be able to set max trans. As a matter of fact, you still can, but Oracle will ignore it, bada boom, and it'll just set it to 255 for all blocks. I would not recommend, by the way, you set a trans to 255. Each one of these trans slots takes up about 23 bytes, and that's 23 bytes of data space not available, because that's coming out of the header, which comes out of the whole block. So yeah, maybe setting it to 10 or 15 for, you know, hot tables might be a good idea. Some blocks may end up with more. Oracle will dynamically add them as it needs it. One interesting thing about trans slots, they never go away. Once allocated to a table, I'm sorry, to a block, not a table. Once allocated to a block, it's always there, okay? It doesn't like say, oh, I'm only using 5 trans slots, now I'll shrink it back down. Nope, nope. If it has 20, it's gonna have 20, done. So that's why I say don't get carried away with this and set it some absurdly high value. All right, any other questions, comments, confessions?
I had some, when I went from 11 to 12, I was getting weight events for the new algorithm, the new memory algorithm. I can't remember the name now. It's escaping me.
Okay.
I was getting a ton of weights with that, and that was what they recommended, is to change the init trans to 5. I think 4.
Yeah.
5. And it was because the new memory thing, it was faster, but it took up more memory. That was the one factor that they mentioned. So, yeah, I don't recommend changing it all the time, but in my case, there was actually a MOS. There's actually a MOS node on it. So at the time,
yeah,
that was at 12. Yeah.
All right.
Rick, I got a question on back to block size again.
Sure.
If you're using compression on a table, do you get better compression ratios if you have a bigger block size typically?
I don't think so.
No.
The way
I'm thinking chance of like data is higher, so you'd get more.
The way compression works in Oracle is it's looking for repetition within the row, right? So it's looking for repeated, you know, character values or numbers or stuff like that, and then compressing those as a key. And then I guess in theory, with more rows, the chance of that repeated key being repeated more in the block. But I'm unaware of any proof in the pudding that a bigger block size, you get better row compression and stuff like that. You know, it might happen, but I don't think so.
That was the argument we were sold for a bigger block size database.
Yeah.
So
What block size are you on?
it was 16.
Yeah, 16 is a good block size, by the way. I mean,
Yeah.
I'm just not real fond of these folks going to 32 and beyond. Well, actually, you can't go beyond 32 now. But you know, 8 or 16, it's probably a decent size. And if you're just not sure, 8 is a really good size. It's a good balance between that small and big. Okay, small being like 4K, and big being 16 or higher. So 8 it gets you a good balance of that ITL ratio, row stuff, And again, most IO subsystems are based on an 8K, mechanism. So you're kind of using the throughput of your IO subsystems, whether they're virtual or real or whatever, about the best.
There is a big data environment with the large tables. So then do you
Yep.
recommend a large block size?
Well, again, if they have large rows, then yes. But just because you're dealing with large amounts of data does not automatically mean that that bigger block size is better. Again, run some tests. I mean, everybody's data is different to some degree. So, what I'm saying might be hogwash for your particular environment, that, a 32K block size really is the right thing to do. But you run some tests and be sure about it. Just don't go, oh, I got big data, so I need big block size. I like big blocks, I cannot lie, again, my little test, even though it was on my little laptop, it still didn't show any significant performance increase by going to a bigger block size. And it would, even on that, I kind of expected to see something tangible, when I went to larger block sizes, both for the indexes and for the full table scan, and yet it wasn't there. So.
You were, if I recall correctly, you were running that on a Windows laptop?
Yeah. So, I mean,
Okay.
it's nothing.
Have you ever made a comparison between that and Mac or Linux?
I haven't, no. And I probably should do that. I've now got, and I've got my new Mac that I have now. I just, I don't know, have you guys played around with the Oracle's VirtualBox thing?
Oh, it's awesome.
That's incredible, man. I just started using that about a couple weeks ago, and man, that's awesome. And
Yeah.
I should rerun these tests on that and kind of get a feel for it. And I just haven't had a system that I can run these kinds of tests on
You
to
need a lot
see
of RAM, though,
this
for
kind of stuff. Is that you, Mark? I can't hear you.
That Mark here, yes. I was just saying that you need a lot of RAM for VirtualBox, because especially with, I think, starting with, is it 12.1 or 12.2? The minimum node size now is 8 gig.
Yeah.
It jumped
Well,
from 4 gig to 8 gig. So you need at least a 16 gig box to be able to run just a single node. And you need a 32 gig box to be able to do Rack Attack.
yeah. Well, I only have
On
16.
mine, which I love.
I have 16 gigs on mine, and I had
Okay.
two 12.2 databases running, no problem.
What size did you specify for the node? How much?
I just took the defaults, whatever they were.
Oh, the default is 1 gig. There's no way it would run on 1 gig.
I have 12 gig.
What's that?
I have a 12 gig on my laptop.
Right, understood. But I'm saying when you spin up a new VirtualBox, when you define the size of your instance, you have to tell it how much memory from your main memory to allocate for that single virtual machine. And I think the default allocation is just 1 gig, which isn't going to be enough to even run the installer.
Well, I had two databases running, so whatever it was
Okay,
enough.
that's impressive. You got two running on
16 gig. It's a 16 gig laptop. I had two databases. I was doing a Golden Gate replication between the two. It was pretty awesome.
Cool. All right.
Yeah, and it worked flawlessly. I was
Sweet,
super
yeah.
impressed.
So Rick, I've been looking at some of the Oracle 20 stuff coming out, and one thing, have you heard about the new automatic zone maps?
I have heard of them.
Yeah,
I really don't know much about it.
I mean, basically, it looks like it's combining sets of blocks. It's kind of like doing a partition, but on blocks.
Right.
And so I didn't know if you had heard anything about that. I mean, I've been kind of looking at it, but I'm just wondering if I'm just trying to see what the advantage is, or
Yeah.
Is it
I
an
guess-
optional feature, or is it something that's always turned on in 20? What? I don't know anything about it, so.
It is not turned on. It's not turned on by default. You have to turn it on by running where is it? EBMS auto _ zone map to enable it. So it doesn't, it's automatically turned off.
Okay.
Yeah, I've heard about it, but I unfortunately know no more than you do. So
I mean, it's like I said, it looks like it's
Yeah.
partition data based on blocks. So it's kind of like setting partitions, but not at an index, but now at a block level.
yeah, well, it gets into their block versus object storage and all that kind of stuff.
Yeah, yeah.
So yeah. All right, I think I'm going to turn the recording off. So whoever's going to watch this, see you next time.
I do have a couple
Yeah,
things.
thank you.
If you want to, I just want to show you a couple